off. I just wanted to, I wrote you also on WhatsApp so that first of all, by the end of this recitation, you have the recitation quiz, right? And then you have another, I think, 3 by the end of the semester. Okay, and by this you will have 10 recitation quizzes, and you are allowed to not solve 2 of them if you have a good reason. For example, if something happened or if you were recruited or something like that. So you can write me a message or just notify me, and I will just take off these two quizzes. And if you need more, so just, I don't know, speak to me. Excuse me? The deadline for this one is this Monday. Yes. No. Yes. No. Okay. Great. Okay, so project 3 is extended. So instead of submitting next week on Monday, you can submit by July the 8th, but please note that your last project, project 4, is by the 22nd of July. So maybe if it is possible to submit during the next week, I think it is better so that you can start working in more relaxed manner on the 4th project, which I believe will be uploaded already by Sunday or Monday or something like that. Okay. So this is it, and the 2 quizzes are planned to be right on the first week after the end of the semester. Okay, and I think that you should, I don't know, discuss with Izal. Commonly in previous years, it was on the same day you had, you begin with the analytical quiz, and then you have like a break of 1 hour, 2 hours or something like that, and then you have the computational one. And I highly recommend to do that and not have like a week between the, or a day between the quizzes, because then you just finish with it, and you know, it really helps that you just leave all of this course behind you, and you know that you did your time. Okay. More time to learn between the quizzes might not be helpful. Okay, just more stressful. Great. So I don't know if Al will let you know the exact dates and the subjects and the materials. I believe that it won't be the material of all the course, but rather like the second part from the coding and so on. Okay, so probably this will be the material, but again, Izal will give you an official announcement. I hope that either through Sophie or by mail or whatsoever. So now today we discuss information theory. Next week we start to discuss the spectral analysis about the Fourier transform and so on. So I'll send you on WhatsApp the dates for next week of our meetings. But if you know nothing about Fourier transform and Fourier series, I highly recommend to come on Saturday to a reinforcement about the sine function, the cosine, and the Fourier transform. Okay, and also if you really feel that you remember nothing, it is also good to come. Okay, so now about information theory. I don't want to explain too much because I think specifically and even more in information theory, the best way is just to practice it, okay? And just start solving the equation. So I'll just say that the idea of information theory was developed by Shannon. It is highly used in various fields of engineering and neuroscience and so on. And this theory is about the transmission of information from one place to another, for example, by using the World Wide Web, right? That you want to know if you have your computer and you want this computer to have a communication with another computer, you need to decide how to transmit the information between them and what is the most efficient yet the most secure way to connect between the two computers, right? So this idea of Shannon was that you have the telegraphs in different places, and you know that you want to transmit a message from the UK to Japan. So you have a number of telegraphs, and you can use physics to calculate the level of of problems and disorders in the connection between the telegraphs, right? So therefore, you want to know if you want to send a message, for example, attack Japan or something like that. So not attack, but let's give a more nice one. Stop fighting, okay? Uh, I hope that this is a better one. So if you want to transmit this message, you want to know that this message will probably arrive its destination from the US to Japan by 4 telegraphs. So what is the best way to transmit this message? And what is the most sufficient way to do it so that you can use the minimal number um, of codes to do that? Okay, I will show you in a minute what does that mean. Okay, and yet that you can still secure it, so nothing will be lost on its way. Okay, and this is why we call it the entropy, right? Because if you think about the telegraphs, so they need to transmit the information from one to another, we are afraid that some information will be lost. So the entropy of each system or each message is calculated by what is the minimal coding of this message in bits that you need to use. Okay, so it is given by this formula, and I want to explain it with a nice example. If I can remember with the example that we did in the reinforcement, that I think that was very, very, very clear. 1 minute. It was here. No, I don't remember the example that we did. Araceli or Sophie, do you remember what was the nice example that we did? Maybe it was we did the shared die. Okay. So let's say, for example, that I play with Austin a nice game in which I want to code what number did I get in my die. When I roll the pair die on the ground, I see the value and I want to transmit it to Austin. And we want to create like a kind of a secret language to do that. So the question is, what is the most sufficient way to do it? By using the binary system. So let's say, for example, the entropy of a pair die is by looking on all the random variables of the pair die. So if I roll a die, I could have either 1, 2, 3, 4, 5, or 6, right? These are the 6 possibilities of my rolling the die. And now I want to tell Austin what is the number that I got. So let's first compute the entropy, and then we can understand what does it mean. So the entropy of all the possibilities of 1, 2, 3, 4, 5, 6 equals minus the probability of getting 1 multiplied by log 2 of the probability of 1 plus the probability of 2 multiplied by log 2 of p of 2 and so on, right? Do you remember that? Great. So the probability of 1 equals 6. 6. 1 divided by 6. And the probability of log 2 of p of 1 is log 2 of 1 divided by 6. And then again, also for this one, right? For each one, it is the same. So therefore, instead of just writing the probability of each one, I can just take this and multiply it by 6, right? Because I have 6 options. So this one is minus 6 multiplied by 1 over 6 multiplied by log 2 of 6. Right? So the 6 and the 6 are cancelled. And then we are left with minus log 2 of 6, which is like writing log 2 of 6. And this one equals, if someone has a calculator, 2 point, it's written here, right? 2.7 or 2.8, 6? I think 2.6. 2.58. Great. So it's negative, the log 2 of 6. This should be positive, but if you use this one, you need to multiply it by minus. And what does that mean? So in the secret language of Austin and I, we use bytes, to communicate with each other. And we want to know what should be the size of the bytes that we communicate with them, okay? So if I see that my entropy is 2.58, that means that each message of ours should use 3 bins. Okay, so we can see it here in a minute. Why is it 3 bins? It's very, very rational. So if I want to code the number 1, then I will use 0, 0, 0. If I want to code the number 2, I will use 0, 0, 1. 3 will be 0, 1, 0. 4, 0, 1, 1. 5 is 1, 0, 0. And 6 is 1, 0, 1. And I didn't use 2 possibilities, which are 1, 1, 0, and 1, 1, 1. So I'm left with extras, right? 1 minute. So what you can see here is that if I'm counting in a binary system each one of my options, I get the exact number that the entropy just predicted, right? If I would just tell you what is the number 1 in binary, how could it be represented, then we would use this, right? 0, 1, 1, 0, and so on. So the entropy is like telling us what is the size of the message that we need to use to tell about all the possibilities of the system. Okay? Yeah, Ofek.
Also, asked without that I thought that we need to round up always.
Yes. Yes, you are right.
But he said that 2.5, that's actually the answer, because in average, you need 2.5.
Right.
No,
So
there is
It is true. So if you want to be on the safe side, so if you use, for example, the telegraph, so each one you transmit, it's like, do you know Morse? So in Morse, like you have a specific number that you can use, and then you just wait in between, and each byte, like for example, SOS is something like that, I think, right? This is SOS. Very, very important to know if you're getting stuck in an island or something like that, and you want to say SOS, this is the way to do it in Morse. So in Morse, for example, you can do it also with fire. If you do like a fast one and then a slow one and then another fast one, but it's really not important. And I still talk about it. Okay, so if you want to be on the safe side, so you want to know what should be the length of each telegraph, so you can say that it needs to be 3, but you can say, wait a minute, sometimes I don't really need to use 3 bytes just to send a message of 0, right? I can use also just 1. And here I can also use just 1, and here 2. So this is what is our meant, that you don't always need to use the maximum length in each transmission.
Yeah.
Yeah. It says you can deduce from it what is the maximum number of bytes that you need to use, but you can use sometimes lower. So on average, you use 2.58 bytes. Okay?
It's
Right.
the average or the
It's-
minimum?
It's the
The minimum time?
it's the average. The minimum to okay. The minimum number that you need for all the options is 3. For all of them. Because here, for example, you need 3 bytes. But for some of them, you don't need 3. You can have only 1. So if you want to refer to all of the options, the minimum is the maximum across them, right? It's this one. So you can deduce it from 2.58. That means that you need at least 3 for all of them. Yet, if you want to transmit only some of them, for example, 3, and you want to be more efficient, so you don't have to use the telegraph and write 010, just write 10. Okay, is that more clear? Okay, so this is the entropy, and here we have an example of calculation for a spare die, and if we have a spare coin, no, here it's not a fair coin. Here we have a coin which is not fair. Okay, unlike the die that it is fair, let's say that we have a coin that it has a higher probability for heads and lower for tails. So how do you calculate the heads, the probability? So you say this is the probability of a head. So this is its entropy, and you add the probability of a tail. Okay, so maybe we should try it like over here. Let's say that in the numbers 1, 2, 3, 4, and 5, the probability is let's do something easy, is 1/8. 1/10, sorry. Okay, this is the probability for each one. This one, and here the probability is half. Then the entropy is calculated differently. For 5 of them, I need to use 5 multiplied by 1/10 multiplied by log 2 of 1/10. And for the 6, I have half multiplied by 1/, sorry, half log 2 of half. Okay? And this one equals to half log 2 of 1/10 plus half log 2 of half. Araceli, can you help us with a computation? This one, by the way, should be lower than the 2.58 that we got before. So when it was equal, this was 2.58, and when it's unequal, like in this example, yes? 2.60. 2.60? 16. Right. And what does that represent? That in most cases, for example, I know that 6 is the most common one. So for this one, I can use a more compact version. So 6 will be 0, 0, 0, and 1 will be 1, 0, 1, right? And since I can use this version, in this type, I don't need to use all the trees. Most of the time, I will use only one bit. And in all the others, I will use the rest of the bits. And by this, in most cases, I don't need to use a lot of information to transmit the information about 6. So this is why this is lower, because I can make it more compact in most of the times. Okay, so here, so when it's unequal, it was 2.16, and there is a theorem that it is always the relation between entropy and the probability, that as the probability is more uniform, then the entropy is the highest, and when it's non-uniform, it's the lowest. For example, if the probability for all of them is 0, this is a very, very, very unfair die. And for this one, it's 1. What is the entropy? 0, exactly, because I don't need to send a message, because it's deterministic. I don't even need to inform Austin that I got 6. I just kind of transmit nothing. Okay, he knows that I got 6.
How many things in the graph?
So over here, you see that the entropy here, the y-axis is the entropy, it's 0 when it's non-uniform, and it's the maximum when it's uniform. So here it's for a coin, for example, the probability. So when it's equal 0.5, then the entropy is the maximum. And when you have an unfair coin, it's the minimum.
Why there is a coin that x-axis is what there?
The x-axis is the probability for heads.
Why the entropy is 1 if I have
The entropy, so if they are equal, so you have 1/2 for a fair coin. It's 1/2, 2 times 1/2 log 2 of 1/2, right? So this one cancels, and then you have log 2 of 1/2, which is log 2, 2, and this one equals 1. Okay? And it is always like this. So now when we have this idea of information, we can use this idea and try to ask ourselves, does the brain uses the same ideas of mechanisms? And when we use information theory in most of the calculations in neuroscience, we don't really use them like the most sufficient one or something like that. But we kind of use these very small calculations to explain something about the brain. Okay, so here, I don't know if we have time for that. Okay. Another thing that now I want us to practice together is what is called the mutual and conditional entropy. This means that if we have if we have two variables, we want to compute the entropy and the relation between these two variables. So for example, I was talking of the entropy of a die, the entropy of a coin, but then I want to ask myself, if I know what was the output of tossing the coin, can I know something about the die, right? Are they related to each other? So in this example, is there any connection between them? No. So these two are independent. Therefore, probably the conditional entropy will be equal to one of them. They are independent, therefore, there's no relation between them. But let's see another example. Is there a relation between the probability of a rain to the number of people with umbrella entering the building? Yes. So if I know the output of the probability of a rain today, I can have some level of prediction about the number of people with umbrella that enter the building. Okay? Great. Okay, so these are the two formulas. For this one, we make two sums for the mutual probability, and then we have log 2 of this. This is for this stage, just look at it as formulas, because I don't want to discuss now what do they mean and what can we induce from them. And here it's a probability, so we just use the probability of one given the other and so on. So here, this is what I meant about fully independent. Again, these are just some theorems, rules that you might need when you want to compute, but let's first see how to use them. Yes, Austin.
I just want to confirm for mutual interest. When it's written P of X, comma Y, that's the same as the interaction or intersection of X, Y? P, X, and Y?
The conditional probability.
Not conditional, above that, mutual.
Here, the mutual?
Yes.
Yes.
The probability of seeing X,
yes.
observation of X and observation of
The
Y.
intersection between these two variables, yes. Let's see an example, and by this example, it will be easier to understand. So let's say we have these two variables, which mean whatsoever, okay? So variable x could have the result of 1, 2, 3, or 4. Let's say, for example, number of people with umbrella in the building. And y could be milliliters of rain on this day, okay? So now I want us to understand how to calculate these things. The entropy of X, the entropy of Y, the conditional entropy of the two, and the mutual. Okay, so let's do it. So it will take me a minute just to copy it on board, so it will be easier to follow. Meanwhile, you can try to copy it also, or look and try to think how would you solve such questions. And if you have no clue, just wait a minute. Okay, so let's see, how do we solve it? So first of all, we are asked what is the entropy of X and the entropy of 1. Just a question, would you like me to explain what we see here on table? Is it not fully clear? Okay, so what we see here is it's called the mutual probability. So what does that mean? So let's have a very simple system, not of the rain and people so on. Let's say these are what kind of things do we have that has 4 possibilities, which are simple, like die and coin? Okay, let's say it's two tosses of coins, okay? So, right, the dreidel. This was, okay, you know, by the way, that the dreidel from Hanukkah holiday, it was a gambling game. Yeah. And you can read about it in Wikipedia that each one of the letters is not, in Israel they teach that it's about the miracle, the happened. It is not true. Each one of the letters is how much do you win when it falls on one of it. So a dreidel is a very good idea. So you have this dreidel, 2 dreidels like this. And they have these 4 letters over here. So it could be 1, 2, 3, 4. And let's say there is this first dreidel here and the second one here. So the probability that you have 1 and 1 in both dreidels is 1/8. The probability that you have 1 and 2 in both dreidels is 1/60. Okay. I mean, like in the second one, the first one is like this. Okay. As you can see, the mutual probability is not always symmetric. For example, here you see 4, 3, and 4. First dreidel, second dreidel. The probability that he will have 3 and this one will have 4 is 0. Yet, the probability that this one will have 3 and this one will have 4 is 1/16. Okay, so this is what the table represents, the mutual probability. For each value, the probability of x and y, which is also, as Austin said, it's the intersection between these 2 probabilities. Okay, for each value. So far, so good. Okay, so now we are asked about the entropy of each one of the variables. So how do we compute it? Any of you has an idea how to do it? Yes.
Do you, the entropy of X, for example, would be the P of, like the sum of minus P times log of P, but that P would be the sum of the X.
Great, great. Christian, you were explaining it exactly as you should. So, now we need to compute something which is called the marginals. The marginals are the main distribution for each one of them in an independent way to the other. So the probability of x having 1 is the probability of this plus this plus this plus this, right? And all of them together are 1/2. It's 1/2. 1/4, 1/8, and 1/8. This is just summing across the columns, okay? And this is called the marginals. So the marginal of x is half for both a and 1/8. And here the marginal of y will be the same by summing the rows. And this will be 4, 4, 4. Okay? Yes, sir.
So why do I calculate all the time the x with number 1 and we don't say in English?
Radar.
Why just doesn't they count the probability of the x axis? I mean, I don't care about, לא אכפת לי כל מה שקורה לעומת הסביבון השני, אכפת לי רק, כאילו רק...
You are right that when I calculate the entropy of this one,
Yes.
I don't care what happens to the other one, but you're given with this mutual probability. Now you want to understand from this how to calculate the two entropies here. So this is an example of a simple exercise that you might have.
So when I have the
Mutual probability table,
I need
yes.
to count for the x-axis, I need all the time that it can be in every scheme.
Yes. You just sum across the columns and the lines. And please note, how could you know if you have an error in summing up? The sum of this should be 1. So here you see 4 plus 4 plus 4 plus 4 is 1. And the sum of this one is also again 1. Okay, so the marginal are always summing up to 1. Okay, so this is the marginal of x and the marginal of y is 4, 4, 4, 4, not 4, quarter. 4 times quarter. Yes. So now, when we calculate the entropy, how would we calculate the entropy of x? What should we do? Right, great, Roxanne. So we use the formula minus, then we look at the first probability here. So this should be the probability of half log 2 of half, right? Plus quarter log 2 of quarter. Plus 1/8 log 2 of 8. And again 8, or I can just multiply this one by 2 because I have it 2 times, okay? And this one equals to 175. It's always use the units of it. Sorry, you don't see it. Any? Meanwhile, would someone like to calculate the entropy of y? This is the easier one. This one equals to y. Yeah. So in a uniform distribution, the number and the probabilities are canceling, right? So instead of writing 4 log 2 of 4 of a quarter, and again quarter log 2 of quarter, I can just take this and multiply it by 4. So this will be 4 quarter log 2 of quarter, and this one equals these two always cancel in uniform distribution, and then the minus goes into the log, and this one turns to 4, and then this one equals to 2. Okay? Great. So this is for the margin. Now, you see until here, right? Not lower than that. Now, let's.
If you use the same, I mean, both of them, you need to use 2 bits, right? Because if you do it on the binary scale,
Yeah.
both of them you will need 2 bits.
Maximum.
0, 0 is 1, and 1, 0, and 0, 1, 1.
Right.
So It doesn't matter that this one is 1.75 because it's also using the 2 bits, right?
So let's see, I can use, if I use all the bits, you are right. So this one will be, for example, 0, 0, 0, 1, 1, 0, and 1, 1. You are right about that. But in most cases, I don't have, when I want to transmit you the message of half, if it was 1 here for x, in most of the cases, I don't need to use 2 bits, right? I can use only 1. So in most of the cases, I don't need all of the rest. So for this reason, we have here something that it is not a round. So you are true that the maximum value is 2. But most of the times I don't need a 2 bits. Okay? So now let's do the conditional entropy. So h of x given 1.
How do you know that you cannot do the same thing with each one with the 2 bits? How do you know that you cannot represent, instead of using 2 bits, just 1 maybe something?
Yes. So the way we do it, we always take the one with the highest probability. And for this one, we use the minimal possible bits.
0, 0.
Yes. Or 0, 1. Both of them are minimal. So when you want to transmit 0, 0, you won't speak with Austin in a collective pen. You would say that in your cards you have 0, 0. You will probably just say, I have 0, and that's it. You use only 1 bit. 1 bit. Yeah?
Yeah, so that would be the same for 2 bits, right?
For
I mean-
2 bits, you have the same probability for each one. Right?
So you cannot choose 1.
And here I can just, most of the cases, I don't need to use all of the bits. Here it's an equal probability. Okay, so how do we, 1 minute. What? Wait a second. Okay. So what we need to do now is we want to calculate of phi of x given y. How do we do that? So now we are doing something different. We are using p of x intersected with p of y, and all of this divided by p of y. Right? So, for example, if we want to know the probability of 1 for x, given that y was 1, so we need to take the probability of the two of them and divide it by 4, quarter. What is 1? Right? And if we want to have 2, so we have the same divided by quarter. And here the same divided by quarter. So I can just take each row. If I want to have the probability of x given y, I will take each row and just divide it by the marginal of that one, right? So when you do that, so over here, for this row, the probability of 1, 2, 3, or 4, given that y equals 1, is all of this divided by quarter is, I have it. Yes. So this one is half, fourth, quarter, 1/8, and 1/8, right? Yes? And now, okay, in a minute we will see it in the conditional entropy. And now the probability again, 1, 2, 3, 4, given that y equals 2, is again, we take each one of them and divide it by quarter. So this one will be quarter of 1/8 and 1/8. And if you continue, so this will be, you don't see it here anymore. So if you continue, the vectors are, this one is an easy one, quarter, quarter, and this one is just 1, 0, 0, right? This is for the same idea, but given y equals 3, and this is y equals, right? And now we want to calculate the entropy of each one. So our formula says the following. The formula of conditional entropy is, because like this in a minute we will see what does it mean. From I equals 1 to 4 of the probability of y multiplied by the entropy of x given y. Okay, so for example, this one is right. Yeah, it is right. So, they don't see me on Zoom. So the probability of y equals 1 is 1 equals 1 multiplied by the entropy of all the possible x's when y equals 1 plus the probability of y equals 2 multiplied by the entropy of y equals 2 and so on. Okay? Now the probability of y equals 1 is quarter. So this will be quarter multiplied by the entropy of the numbers that we have are half, quarter, 1/8 and 1/8. This is for this one.
You just said, you can also see that the P of y always sum up to 1, so you can just substitute it, right?
P of y,
P of y,
yeah, but the entropy of each one will be different. So this is why you cannot just.
okay.
And for the second one, it will be 1/4 multiplied by the entropy of 1/4 1/8 and 1/8, right? And so on. And we know how to compute this, right? It's the formula of minus the log blah blah blah.
We've already done it.
What?
We've already done it.
We've done this one?
Right.
The marginal here, but in this one, so this is quarter multiplied with this, but it might be different. It's just
Yeah.
a matter of luck.
Yeah.
Okay, so this one equals by the end to 1 and 3/8 bits. Okay? Correct.
3/8 or?
3/8, yes.
This is for.
Maybe it would be easier like this. 11/8.
This is for all the, for.
Yes. This is the conditional. Are you ready for the last one?
Wait, can you say again what it means? It's give you information about x while I know y.
Yes.
All right.
Yes,
To give you the information about X when I know Y, if I will need 11 and divided by 8
Yes.
bits.
yes.
To be-
Let's say that in the game of the dreidel we're just talking about, one dreidel is mine and the other one is of Austin. And let's say there is some connection between these dreidels. In the dreidel ID, they are independent, but there might be a relation. So let's say that Austin's rows is a dreidel and then it falls over the number of 3. And now I want to transmit to Austin what is my dreidel. So what is the entropy of my message? This is the result. Okay, because he knows the result and I don't. Great. So again, now it's still a bit hard to deduce from it if these two are independent or dependent. Now we are still at the level of the formulas. In a minute, you will have a break. We'll just finish with the mutual entropy. Okay, so for the mutual entropy, you can use one of the two formulas. In mutual entropy, you can use one of the two. The first one So the first one is using the direct formula, which says that this is the sum of the sums for all y and all x of the mutual probability of x and y minus 4 log 2 of p x and y, which means that we take for the entropy, we just take each one of the values in this matrix. Okay, so it will be 1 over 8 log 2 p x p log 2 of 1 over 8, 1 over 16 log 2 of 1 over 16, and again for all the values in the matrix. Long, and I don't want to do it. Okay. Another possibility is to use the chain rule. The chain rule says that there is a relation between the mutual entropy and the conditional entropy. So the mutual entropy equals to the entropy of x plus the entropy of x given 1. Again, these are coming from mathematical proofs that I don't want to go into them. The information theory is a very large mathematical field, and we just want to know how to use it. Oh, sorry, I didn't hear a mistake. It's not x given y, it's y given x, of course, because it's what I know about x and what y could add me, what more I could be. So we know that h over x was 1.75, right?
Yeah.
And h of y over x is 11 over 8, so 1.75 is like 7 over 4. So that the two of them equals to 27 over 8. Okay? Yes, sir. Sorry, you are right. I mistakenly written the wrong. So it could be either this one or the other one. H of y plus h of x given 1. You are right, so. So if we use this one is 2 plus 11/8, and this one equals to 27/. Okay, now maybe we do want to say a word about independency between the two. So the only thing that I want you to know is that before we go into mutual information, which is the golden goal today. So if y of x is smaller than the entropy of x, then we can deduce that they are dependent.
X and Y or
So y is dependent on x. Okay? So it's true that no, sorry. I always write you the wrong way. So if x given y is smaller than the entropy of x, this means that yeah, that they are dependent. You could have it in both ways, either that y dependent on x or both of them are dependent. X and y dependent. Okay? So, for example, in our case, we had f of x given y, this was 11/8, right? And h of x was 2, 7 over 4. Is this larger? So this one equals to 14/8. So yes. Let's see the other way around. H of y given x is 13/8. And h of y is 2. And here we see it again, that this one is smaller than this one, then they are dependent. Okay? What does that mean? That they share some part, that if you know the part that they share, you can deduce about the other. Okay, and this is just about mutual information that after the break, we will see the exact calculation. Okay?
like the second one, so what is that? Compatibility will not be true.
It might, if
And
they
the
are,
one
okay,
true and the other not.
if they are independent, then the entropy of x given y is h of x, right? This is the fully independent, then yes.
And like the
If
one
they are fully independent, if x and y independent, then h of x given y just equals h of x. Y says nothing about x, so I cannot deduce from y anything about x. So this is what it is. And just maybe if you want to connect it to the brain, the basic idea is that you can ask yourself, does neurons, if for example there are a few neurons talking with another neuron, for example in Parkinson and things like that. So to what level each neuron contributes to the information? If we can take this idea of entropy and use it on neurons, we can deduce how much information each neuron has, right? So this is one way of use. And the probabilities that we use are commonly the firing grades. Okay? Do you want a break or do you want to ask question? What do you prefer? So maybe just the last one.
I thought it was all great.
Okay, great. So take, do you need 10 minutes? Come back here at 3 and 10. 3 and 10, I go on with mutual information. Okay. כאילו זה אומר לך כמה היום נמצא חזק. בוא נגיד, בוא ניקח
כאילו שאנחנו רוצים, כאילו אנחנו רוצים משהו על Y, ואז אנחנו רוצים שאנחנו יודעים, אבל אנחנו רוצים להעביר את X.
בעיקרון זה מה שאומר הטרנד.
אבל זה מה שזה מוזר, אם זה נכון, אז בעצם אני צריך לא להוסיף, אלא להפחית. נכון? כי אם נדע על Y.
אז זה, כאילו, זה מה שאני מנסה במיוחד של הנתונים. וזה לי בעניין שבעצם עד עכשיו דיברנו על N. כאילו, זה קצת מצב. אין פה כאילו,
אני מוסיף בדיוק לראות שאני יודע יותר.
זה מה שאנחנו נעשה במיוטואל.
אבל אמרת שזה מיוטואל, לא?
זה המיוטואל, N.
מה
כמה ביטים אנחנו צריכים כדי להעביר את המידע על המצב המשותף שלנו. כלומר, אם אני רוצה עכשיו להעביר לך מידע על זה שהיה גם אחד וגם אחד, או 2 ו1, אז כמה ביטים אני צריכה? mutual information יש בדיוק ההחסרה הזאת. כלומר, בהינתן שאני יודע משהו על אחד, כמה תוספת אני צריכה כדי לקבל את זה? זה אולי גם בקונדישנל.
לא, אני גם, אני כאילו באיזשהו מקום מרגיש שאני מתגלגל לקונדישנל והמיוטואל, וכאילו, כי המטרה של מיוטואל, כמה ביטים אני צריך, אני חושב כמה ביטים אני צריך בשביל להעביר את המידע על שניהם. אבל אם אני יודע משהו על כמו אני יודע מה, אני יודע מה,
נכון.
אז למה אני צריך להוריד? אני צריך להוריד. אני יודע וואי, לא בעצם אני צריך להוריד. כדי לקבל את X.
אבל אני צודק, כדי לדעת כמה אינפורמציה.
כן.
מה מידע
צריך, כאילו, זה... יש הבדל בין גם Y סביב Y? כן, כן. לא,
All of my sarcastic answers were on.
ככה זה נחמד, אבל אז שאתה רוצה לכמת את זה, ואז פה זה מתחיל להיות הבעיה.
אני אגיד לך את האמת שב-information theory,
לעמוד על דברים לא מקום. הבעיה לא...
למה לפרוביליטי?
הבעיה לא, להכשיר איזושהי נוסחה, כל הדוקטורים האלה, אבל זה בלי... כן, בלי GPT, לא, זה קל לי GPT. לא, לא מדבר על
GPT. You make a function that this is the entropy, right? You just take this one, that it takes the sum of the pi log 2 of pi. across all the islands. This is not a hard one to create, right? So given the
But
fees, you can
Ah.
calculate the entropy. So I think it's even easier to do it when you have code, because instead of writing.
No, of
all-
course,
Yeah,
it's much easier because it's in the loop.
yeah,
כן, אבל נגיד כזה, כל שהוא בפטן, תלוי שבהינתן, כאילו, לא, זה מסובך, כאילו, שים את זה בקוד.
בגדול הפעולות פה זה פעולות חיבור, חיסור, דברים כאלה. ופשוט צריך לדעת מה אתה עושה. מה? אין, פה אתה לא יודע אם יש חיתוך ביניהם. עכשיו אנחנו נמצא את המדד בכמות חיתוך.
למה? שאין חיתוך ביניהם.
למה?
זה, נכון, זה שווה לפי של, זה הולך x, y, כוואי, נכון?
נכון. ואם אין חיתוך אז שווה x כפול y.
נכון.
ואז ה-y מתקדמים, וזה שווה לפי של x, זה לא מדד.
אם זה שווה לסיים.
אנחנו אפילו יודעים שיש חיתוך ביניהם לפי התרגיל. אורית, בתואר ראשון, אין לכם את הדברים האלה? עזוב אנטרופיה. אין לכם את כל הקונדישיונל... פשוט לא משתמשים בזה.
למדנו את זה, כן. לומדים את זה בהסתברות ברמה, כאילו זה הרמה הכי גבוהה שמגיעים בזה בהסתברות. כאילו הבייס זה הכי גבוה, ולא נוגעים בזה משלב, כאילו לא משלב, לא, אנחנו נתחיל לזה. אנחנו נתחיל שכאילו שאנחנו לא יודעים.
את זה, אני מרגישה שסוגים כאלה מבינים ואני לא יודעת פה.
אני מבין. אבל גם חוץ מסתברות שם, לא שזה כזה מסובך, מסתברות שם, כאילו. זה לא באמת חוץ מסתברות שבונה לכל תקופת האחרים. כאילו זה.
זה פוגע בכם.
תגיד על הכל. כאילו לא רק זה, זה הדבר האחרון שעשינו קורס בעברית סמסטר שעבר, שכמובן כאילו זר, אני חושב שאנחנו באים עם ידע מבוסס מהקורס הזה, כאילו לא.
למה? אבל זה, לא, רגע, הקורס של עיבוד הקוד שהיה לכם יהיה עכשיו, בנושא של אנליזה ספקטרלית. אפשר בכוונה משאיר את הסוף, זה הקורס שיש לכם הכי הרבה ידע.
אז לצורך העניין לנו לא, וכאילו משהו לי לא, זה היה היום של השמיטות, נפלו מלא שמיטות, אבל יום שני לא למדנו כמעט, כאילו לא עשינו PCA,
לא, PCA בסדר, אבל את כל הנושא של...
טרנספורמציה תפויה,
לא, נכון.
אני לא יודע, כאילו, אני יודע שזה לעבור במפה בסדר לערב, שקונבולוציה פה, זה משהו שם, לא יודעים, לא נכנסנו, לא מפריד בכלל, כאילו, מגיע בכלל לא, גם זה וגם כאילו, ואמרו שעשו עוד, ועשו פנסים, כאילו, ועשו עוד.
אבל עכשיו נגישות אתם אומרים,
נגישות היה.
הסמסטרלי,
גם,
לא נכון.
אורית, לא היה זמן.
אז מה אתה שם בייס במודלים?
כן, לא היה מלחמה, לא הספיק איתו, כאילו, PCA,
אז כאילו דרך שהכל
PCA זה הדבר הראשון שמורידים. גם בעיבוד אותות זה הוריד את זה, גם בזה, הדבר הראשון.
סבבה, ממש. טוב.
Oh, I gave you too much time.
Okay, guys, let's do it. So, the next thing that we are going to calculate is called the mutual information, right? Because so far, the only thing that we could say about two variables is if they're independent or dependent, right? This is what we know, and we could I'll give you a clue, you don't need information theory to deduce that, right? You can use other things, for example, if you take the probability of X and Y from the mutual probability, and they are independent, then only if they are independent, it's the probability of X times the probability of Y. Okay? So, as I said, we don't need entropy to deduce whether two variables are dependent or not. But the new thing about information theory is that they tell us how much they are dependent on each other. Because if you say, for example, that we have the two variables, the relation between two variables could be like this. This is X, this is Y. It could be like this. So they have a possible overlap. And it could be that Y is fully dependent on X. So that if I know something about X, I don't need to transmit more information. I can just know exactly what is the Y. Okay? And information theory tells us what is the level of dependency between them. Because it has a new way to do it, which is called the mutual information. So the mutual information between X and Y equals to the entropy of X plus the entropy of Y minus the mutual entropy between them. Okay? So let's see, we know
What is the meaning of the I of entropy?
this is the definition.
This is the definition of the function.
Definition,
It shows us how much the relation.
yes, of mutual information.
Wait, but
So this means that if I want to know how much they overlap with each other, I can calculate the mutual information. Let's see, within 1 second, I'll show you the different probabilities, the different things, okay?
why can't we, like, if we know they're independent, why can't we take the P of X and P of Y?
I didn't say that these two
No, no.
are,
You said that until information theory, we couldn't like, estimate how the mutual.
yes,
But what if we'll take the P of X and P of Y
yeah.
and subtract their, how do you say?
So this is based, if you know, on the, this is called unifying, this one, right? That the unifying between two variables, you don't see that, equals to A plus B minus the intersection between them. It is true that the information, the mutual information is based on this, but it has no a value. This one has no value. These are just groups. Here you have a value that you can quantify. Okay, so let's see, just 1 minute, let me show you
No, I,
all the rules that are deduced from this definition. Okay, so let's start first of all with more ways to calculate the information. So we know the chain rule, which says the age of X and Y equals 1 minute. I don't want to confuse you once again. So H of X plus the entropy of Y given X, or H of Y plus the entropy of X given Y, right? So therefore, we we can deduce that the mutual information would also be written in the following. So I of X and Y equals, for example, to H of X plus H of minus H of Y given X, right? Can you see why? Sorry, no, H of X given Y. Right? Or H of Y minus the conditional Y given X. So by this, we have a quantification of how much information do they share. So this is why this is called the mutual information. Now, when the mutual information, if the two are fully, if they equal to each other, so if we have X, I can't see what I'm writing. X equals Y. Then the mutual information of X and Y is of X, and this one equals to, for example, H of X minus H of X given Y, and H of X given Y, since they are the same, so this one equals 0, so this is just H of X. And 1 minute, where is this one? Okay. Now, if they are independent, okay, then we have the following. We know that if they are independent, then the mutual entropy is the sum of H of X plus H of Y, right? So in such case, the shared information equals 0. So now we can say the last important thing is that the mutual information is always greater than 0 if they are independent, and if it's equal, it is smaller than the minimal entropy of H of X or H of Y if X contained in Y or Y contained in X. Okay? And now, in the last 10 minutes that we have, let's see an example. There are so many examples in the is it this one? No, I want to have, okay. No, not this one. I want to have, this is, by the way, the question that you asked me about the ROC that has also information. So you have it here, but I want to show you a one that is very much is R-like type. So you can try today, if you feel that you didn't fully understand, try to solve more questions. And you have also the recitation quiz. Yes, Julia.
I was wondering, is there any relation between usually information and correlation?
So, okay, this is a very, very, very good question. Do you want us to discuss it shortly now or after?
After this.
Okay, so let's do it after because I think this will help to understand it. Okay? So let's say that we have a disease called, well, you know this disease, testis nervosis. And this might have two symptoms, for example, crying and, I don't know, becoming red, something like that. Let's take this too. And we have here a table which describes the probability of each one of these symptoms. So, for example, if the patient is showing both S1 is not showing either of the symptoms, it might still have the testis nervosis, even if it's not red and not crying. Okay, for probability of 0.4. It might be only crying, but not red. And then this is the probability of 0.3. And it might be red, but not crying, 0.1, or both of them at any stage of the quiz, even after, with 0.2 probability. Yes.
How come not having the symptoms has more probability of having this nervosis? If you would expect that having at least one symptom really gives you more probability to.
So also in real, it's a good question, but also in real diseases, you don't always have symptoms, right?
Or it could be a happy symptom. Like if you feel like S2 is like smiling all the time.
Yeah.
Or like going for ice cream. Like yeah, like it's less likely that you do both of them, you know, different.
Okay. Yeah, sorry.
No, I just said like maybe just another symptom like raised heartbeats or something like that. That's just not in the table, but it does also.
This is also true.
Yeah.
Okay, so now let's say that we want to say what symptoms, let's say that I'm sitting on the second row and Izal wants to tell me about each one of you. Does he suffer from testis nervosis? Okay, so he transmits me a message with a number that indicates for each one of you. We have a table, the same table, and he wants to indicate for each one of you if you suffer from testis nervosis and what are the symptoms that you show. And we have two ways of decoding such ID. So the first one says that there are 4 possible values. For example, for each one of you, it will tell me whether you don't have any symptoms or you have only S2 symptoms or you have only S1 or both of them. So 4 occurrences. And in the second one, instead of telling me what is the exact symptoms that you show, it just tells me if you don't show a symptom, if you show one of the two, or if you show both of them. Okay, so in the first way, X is 4 possible values and Y is 3 possible values. Okay, let's start by calculating the entropy of X and the entropy of Y. How would you start? This is, by the way, from an exam. Right, so let's start with the easier one. Okay, so for X, sorry, we know that we have 4 probabilities. H of X, and we know that X is 0.4, 0.3, 0.1, and 0.2. Right? 0.3, 0.4, 0.1, 0.2. 0.3, 0.4, 0.1, 0.2. 0.3, 0.4, 0.1, 0.2. 0.3, 0.4, 0.1, 0.2. 0.3, 0.4, 0.1, 0.2. 0.3, 0.4, 0.1, 0.2. 0.3, 0.4, 0.1, 0.2. 0.3, 0.4, 0.1, 0.2. 0.3, 0.4, 0.1, 0.2. 0.3, 0.4, 0.1, 0.2. 0.3, 0.4, 0.1, 0.2. 0.3, 0.4, 0.1, 0.2. 0.3, 0.4, 0.1, 0.2. 0.3, 0.4, 0.1, 0.2. 0.3, 0.4, 0.1, 0.2. 0.3, 0.4, 0.1, 0.2. 0.3, 0.4, 0.1, 0.2. 0.3, 0.4, 0.1, 0.2. 0.3, 0.4, And then h of x is minus of 0.4 log 2 of 0.4 minus 0.3 log 2 of 0.3 and so on. Right? And this one, oh, I'll close the, no, I don't want to close. Okay, you'll just see it. And this one equals to 1.80. Okay, so in most cases, when he tells me something about your condition, what symptoms do you show, he needs to use, he can use in many of the times, he can use only one bit. For example, telling me Amit 0, Austin 1, Ella 1, 1, okay, and so on. But in some cases, he needs 2 bits. So this is the entropy, 1.84. How do we calculate h of y?
Take the probability of 0.3.
Yes,
0.2 is n of 0.1.
yes,
The 2 in the middle is 1.
exactly. So this one equals to the entropy of 0.4, 0.3 plus 0.1, because they are linked together, and 0. And this one equals 1.5. So as expected, it needs much less, most of the time we need much less bits to tell me what is your condition. Because now,
How much, right? Because say what three summing at 1.
no, here it's 0.3 for symptom 2 and 0.1 for symptom 1. But if you want to use them as the same, just saying if you have one symptom or two, so we just sum up the two probabilities together.
So just your one thing for the
Yes. Okay. So the next question is, what is the mutual information between the two variables? And I can tell you this is the kind of thing that Izal likes to say, you don't need a calculation. Why? So I'll just write here, just in case you want to remember, I of x, y equals the entropy of the first plus the entropy of the second minus the mutual entropy, or we can use the chain rule and do just for one of them. H of, oh, I'll always forget it forever. Right? It's given X or given Y? Given Y. What is left of X when you know X from Y? Yes. So how should we do this very frightening exercise without any calculation? Yes. Who has an idea? What is the relation between the two distributions? Yes, Jude.
When the first symptom is negative, what is the probability of having a positive second symptom?
Right. This is what we do if we want to go like straightforward, just using the formulas. Okay.
Yes.
But I want you first to think what should be the result. Yes, Austin.
It should be
1.5. Right. Why?
because they're fully dependent on each other.
Exactly. Because if I know X, then I know everything about Y, right? But if I know Y, do I know everything about X? Right, so the neutral information is the entropy of Y, which is the smaller one. Right? Because you can deduce between them. This is just about the ID between the two, between mutual information. Because what? What do you mean that they're random? So if I know about someone, if he has this symptom or this symptom, then I know if he has one symptom, right? This is the ID here. So if you know X, you can deduce, if you know this table, you can deduce everything about Y. But if you know Y, you cannot deduce about X.
If they were built from the same, like if you
Yes.
had two different tables, then you wouldn't know anything about the other.
Right.
Because they were built from the same table and X is the most comprehensive out of the two, then you know everything about Y because X is the most.
Exactly.
Why
So
do you take the smaller X and why do you take the 1.5? Why don't you take the one?
So the mutual information is to what level does the information that they share is the same. You understand? So
Because if I thought about it, I would say that it's 1.84 because.
Right.
say, okay, I need all the information, tell me about Y. Why can't you tell me about X? So I will say
So-
more bits.
the mutual information is the intersection between them. So the intersection between X and Y equals Y. So therefore, the mutual information is of Y. This is how much information they share. Yes, Austin.
I was just gonna add, one thing to also recognize is that the mutual entropy, which is similar but different, that's 1.84.
Right, exactly.
Because that represents all the information that you would want to express.
Exactly.
The mutual information is just the smaller area, which is equal to, not, area meaning going back to the circle,
Yes.
but the smaller amount of information
Yes,
from each other.
exactly. So, and now if we, anyhow, if we still want to calculate it, so let's see. So, one way is calculating age of X. No, here I just use the fact that they are known. Yeah, so I did the fact that they are dependent, I just used it, but I can say I don't want to, yeah, this is the updated table. So, in such case, if you want to start really computing these two, it gets really complicated very fast. If you just don't use the logic, because if you want to calculate the entropy of these two, now you need to take these two distributions and create, for example, the mutual probability table. And this will take you a very long time. So another way is calculating the probability, the conditional one. But then it's a question of how do you do it? Because again, you need to multiply the probability of X given Y is P of X multiplied by P of Y, and this one not multiplied by intersected with P of Y, and then this one is divided by P of Y. Okay, and if you do this again, you need to calculate everything. So we can do it, but it's a bit of waste of time because what you need to do when you look at such a question, you first need to ask yourself what should be the output. Okay, if you still want to use the formulas, so
I really recommend going through the recitation notes. So for example, here, I think this is a very, very, very nice exercise to start with. The relation between spikes and probabilities and so on. And so maybe try to do this one. It will be much more easy to calculate it in full. Okay? And that's why to solve it itself, we have 3 exercises. And that's it. Now, Giulio, sorry for taking so much time from you. So just to the question of Giulio about the relation between entropy and correlation. When, it's a very good question because this is one of the best thing about signal and data analysis, that we want to see if 2 signals are correlated with each other. But sometimes you have only one value. For example, the probability of something. This is only one value. And then when you want to know if 2 things are connected to each other, then you use mutual information. Okay? So if you don't have a distribution, or you don't have a time course, or an activity or a vector or something like that, then you use information theory to deduce about the relation of the 2. Great. Okay. Thank you. Thank you for your patience. Oh, they left.